Okay, let's see. Is this better? Okay. Okay, so I'd like to thank the organizers for inviting me here. It's actually fun to be here in this part of Germany because it's very close to my home where I grew up in Bremen. So, okay, so what I'd like to do in the next 30 minutes is tell you about work that we've been doing in my group at EPFL with collaborators, in particular those that are listed here, Paul Seidel at IBM, John Bowers, late Marco Rodetsky, and Christian Kuz, on developing what I like to call hybrid integrate nonlinear photonics. And I'd like to point out the activities in the field that encompass not just chip-scale frequency combs, but in general, there's really a remarkably fast development ongoing of miniaturizing nonlinear elements. So what traditionally was bulk fiber optics, bulk crystals can now be miniaturized on chip, manufactured with wafer scale manufacturing, and also is slowly making a transition, okay, to real world large volume applications. And that's the story I really want to tell you today about hybrid nonlinear photonics. Okay, so what I'd like to start with is there's been a lot of discussion already, a lot of tutorials on optical frequency combs. And what I'd like to highlight here and discuss is the story of how you can miniaturize these. And I'd like to tell you about the physics that goes into miniaturizing frequency combs, some of the technology development that we have to do, and some of the applications that these devices can be used for. So optical combs, again, have been invented by Ted Henge and Hall, of course, contributions by many others. And what they effectively are is they provide links from the RF to optical. And much of the early excitement about optical frequency combs came from the fact that you could connect finally the radio frequency domain with the optical domain in this bidirectional fashion, where you can either synthesize an optical frequency from a radio frequency or divide down an optical frequency from or generate a radio frequency from an optical frequency. Now, what is interesting is that despite optical combs being almost 2-decade-old technology, it is now understood that optical frequency combs, in fact, are remarkably useful tools for many applications, not just frequency metrology. And they can be used for LiDAR, they can be used for spectroscopy, they can be used for ultra-fast distance measurement, and so on. And in many applications, you do not actually need self-reference optical frequency combs. Now the question that comes into mind is what does it take to make optical combs a ubiquitous technology, so that is used in many applications in the real world. And if you look a bit kind of at history, what you see is that over the last, say, 20 years, optical fiber laser frequency combs are still kind of a rather precious commodity to come by. Menlo Systems, that has commercialized fiber laser frequency combs, has sold about 200 or 300 units in the world. And so this tells you about the scale, actually, that these are still deployed. So these are still a technology that is not yet ubiquitous. And so the vision that my lab, but also many other labs in the world have really come to work on, is the question: can you miniaturize optical combs in the same way that you can miniaturize MEMS sensors or many other of the electronic devices that we use today? And so the idea has been, can we shrink down an optical frequency comb, such as the RF to optical link can really be fitting kind of in this little kind of packaged housing and manufactured with semiconductor processing techniques. And this technology, or this is possible today, and I would like to take you kind of the journey of developing these so-called microcombs. And these are, I'd like to highlight some of the differences and also the physical parameters and principles that go into making these optical combs work. And so some of their key features are that, again, they can be wafer scale, but also they access very high repetition rates in the tens of gigahertz domain. Okay, so what is the principle of generating these microcombs? So the way we generate microcombs is using a very old process, and that is of parametric interactions. And so for those of you who are a bit familiar, actually, with nonlinearities in the superconducting domain, already in the 60s and 70s, JAWS and parametric amplifiers were developed, okay, in the microwave domain to amplify microwave signals. And while in the microwave domain, using JAWS junction, the nonlinearities can be very, very large. This is not the case for the third order nonlinearity of glass or in general materials. And this Kerr nonlinearity is typically very weak. And the Kerr nonlinearity in, say, optical fibers gives at its lowest level rise to 4-wave mixing. So where at sufficiently high intensities, 2 pump photons are annihilated and a signal and islet photon are created. And this process evidently needs to satisfy energy, and so it will generate a pair of equidistant sidebands. Now, generally these processes are very weak, and you can enhance them. And the way to enhance them is to use an optical cavity. And I'd like to talk today about using so-called photonic chip-scale microresonators for that purpose. And these microresonators have a free spectral range, so the inverse round-trip time of light. And with this, you can enhance, the optical fields inside the resonator. And if you now pump one of these optical high-Q resonances, what you have is parametric fluorescence. That is to say, two photons are annihilated and two sidebands are created. And once that rate of parametric fluorescence overcomes the cavity decay rate, you have parametric oscillations. And parametric oscillation threshold, in contrast to a conventional kind of laser, scales with the inverse of the quality factor squared. So the losses actually enter quadratically. And this is due to the fact that it's intensity-dependent gain. And so this implies if you have a high-Q optical microresonator, you can generate, in fact, very low thresholds for these parametric oscillations. And so, this process gives rise to optical combs. This was discovered now more than 15 years ago, but also tells you kind of the time scale it takes from an idea to go from the lab scale to actual transitions into actual commercial deployment. And this was an early experiment where a silica microresonator was used and pumped and generated a very broadband spectrum using this parametric forward mixing process. And at the time was shown that the sidebands are completely equidistant. So this process, which just used the nonlinearity of an optical fiber, can provide, without a mode locking mechanism being present here, still an optical frequency comb. Now these combs are called Kerr combs because of the Kerr nonlinearity, and they have been observed in virtually all the platforms. So be it platforms that span silica to crystal resonators, to even fiber cavities, to 3-5 compound semiconductors, to even materials with second order nonlinearity such as lithium niobate. And all these kind of devices, what you use is resonators to enhance the buildup of optical field inside the device. And so in some sense, these Kerr combs are a very kind of natural process to look for in all these devices. Now, there's one caveat with these optical Kerr combs and with this frequency comb generation mechanism, and that is that, in general, the interplay of forward mixing can be very complex. Okay, and so without going into too much detail, let me just mention that this beautiful cascade of sidebands that I mentioned, that gives rise to an equidistant optical comb, is actually not the case for cavities that have low quality factor, that is high dissipation. In cavities that have high dissipation, what typically happens is you generate sidebands, that form a primary comb, and then through non-degenerate forward mixing, you generate subcombs that, upon pumping further, can merge into a whole kind of series of many, many thousands of comb lines, with erratic spacing. And so, generally, it's a chaotic waveform. And this chaotic waveforms actually are produced primarily in devices, but the cavity decay rate kappa is actually quite large compared to the dispersion. And this is the case for most integrated platforms to date. Now, so this formed an impediment for many years until it was noticed that you can even generate a stable pulse train from a chaotic waveform. And that is by making use of kind of a soliton formation process, so-called dissipative Kerr solitons. And so in this case, I show an example here of a crystalline resonator that's kind of half shown that was pumped with an optical fiber. And if you look inside at the output spectrum, what you find is that the moment you pump the resonator with light, so you see a slight drop in transmission, you see first a chaotic region where the repetition rate beat node of the comb becomes very broad, so it's a noisy state, and a broadband optical comb forms that, however, has very little coherence. And if you tune further, you see something quite remarkable. You see kind of a series of equidistant steps, like a quantization of the intracavity field. And each of these steps, we now know, is due to the formation of dissipative Kerr solitons. And so these solitons are solitons, not in the conventional sense as a known optical fiber, where you have a Kerr nonlinearity that's balancing dispersion. But in our case, the solitons actually have a presence of loss. The cavity is a lossy medium, so you have a dissipation term here. We also have a laser detuning, so the laser itself actually can take different values, from cavity resonance. And also we have a pumping term. So these solitons are solutions of a driven dissipative nonlinear Schrödinger equation in the presence of a detuning and a drive. And these are called dissipative solitons. And you can simulate the dynamics of these solitons. What is happening is that the moment you pump light into a cavity, you first have a region where you have modulation stability, so where the continuous wave laser breaks up into a periodic kind of modulation, okay, of sort of Turing rolls on the resonator. It's then followed by a chaotic regime. So this chaotic regime can be again thought of as all these 4-wave mixing sidebands generating this incoherent waveform. But then something very striking happens when you tune through resonance and become bistable. The cavity field solution changes and you form stable solitons, either 1, 2, or in this case here, 5 solitons. And these are very short pulses, okay, whose distance is fixed in time. So they're locked, and they're locked towards a CW background. So these are not freely floating solitons inside the cavity, but in fact they're locked on the continuous drive actually that's present in the cavity. And so this shows kind of a very general principle that one has seen also in other phenomena. It's a phenomena of pattern formation. And pattern formation is not something that exists only in a nonlinear system. It's truly ubiquitous in biology, in chemistry, in thermodynamics. And the moment you have a thermodynamical system that has nonlinearity, that is driven out of equilibrium, patterns form. Okay, and this is an example of a very famous one here from Soliton Cherenkov, who studied this in the context of chemistry. And so in some sense we can think of these dissipative Kerr solitons just as solutions of this out of equilibrium pumped optical resonator. Okay? And historically the solutions in these microresonators there satisfy a very simple equation. This is called the Lugano-Lefebvre equation, which was taking some ideas from thermodynamics into optics, okay, and admits as solutions as dissipative solitons. Now what is interesting in these optical resonators is that one can trace the stability chart of these solitons very precisely, because experimentally one has the pump power, okay, and the detuning of the laser as 2 parameters at one disposition. So one can control where the laser is positioned compared to the cavity and how much power you have. In this case, you can trace out, okay, different boundaries of the different solutions that this equation admits. And you have a chaotic regime, you have a solitonic regime, and you have also soliton breathers. And this chart here, okay, is a solution of the ideal, okay, Lugano-Lefebvre equation. In reality, there are many imperfections that need to be added, and the stability chart can be much more complex. It can admit much more phases. You can have soliton crystals, you can have breather solitons in stable regimes, you can have many bifurcations even in the solitonic regime. And these can be studied actually experimentally, okay, in these systems and compared to theory. Now, there's also a lot of so what are some of the properties of the dissipative Kerr solitons? So their salient properties are, first of all, that the repetition rates can be very high. So the repetition rate is just the inverse round trip time of your cavity. So that can be as high as tens of gigahertz. In addition, you have short pulses, so they can be as short as a few optical cycles. And the spectral envelope can be predicted by this Lugano-Lefebvre equation. And the pulse duration itself actually is also tunable by detuning. So as you detune further the cavity, actually the pulses become shorter. Now, these dissipative Kerr solitons have seen a renaissance of studies, okay, of nonlinear dynamics, and opened a very controlled system to study nonlinear dynamics. And I will not go into detail, but I want to share with you that over the last years, a lot of the excitement came from the fact that many phenomena were observed experimentally in a lab that could not be predicted by a simple Lugano-Lefebvre equation. And so one had to go back into the equations and ask what term is missing. And many observations that include, for instance, the Stokes solitons, soliton crystals, breather solitons, Raman cell frequency shift, all these kind of are phenomena that have been observed for the last years, okay, or soliton switching, and been explained by modifications of the underlying theoretical framework. So there's a lot of nonlinear dynamics that was discovered, many of it, as mentioned, which was not theoretically kind of predicted or anticipated. So today we have a very, very good understanding, actually, in the field of these dissipative Kerr solitons. And we're going to ask the next step, which is, what does it take, okay, to really make these solitons, okay, in microresonators a technology? Yeah? And for this, I'm switching now from the fundamental nonlinear dynamics to something much more applied. The question I want to ask is, what does it take to move kind of this, lab inside a chip, okay, to a chip really, or chip in a lab to a lab on a chip? And if you look a bit at technologies that encompass our daily lives, be it MEMS, be it magnetoresistance, or silicon photonics, all these technologies, they start in academic research labs. MEMS in Berkeley in the 90s, okay, magnetoresistance in Europe, okay, then silicon photonics started in Berkeley, in Santa Barbara. All these technologies within 2 decades transition into commercial use. But what they share is the feature that they are integrated. That is to say, they're manufactured using wafer scale processing that allows very precise, controllable, high yield, high volume production at very low cost. Now, secondarily, all these technologies would never have worked if they're not low power. So the technologies are required to operate with power levels that can be sustained, particularly in handheld devices, so need to be very, very power efficient. And when it comes to optics, what's really important is that we have the laser also on the chip. And what I'd like to tell you is, in the next part of my talk, is how to move these research of microresonators into a realm where one can use it for actual widespread deployment and address these challenges of integration, of power, and also of integration of the lasers. And so the first thing I want to address is integrating the optical resonators on a chip. And so, whereas many of you know that silicon photonics is a commercial technology, you can design a chip, send it to global foundries, and have it in say 6-8 weeks back and measure it. The problem with silicon is it's remarkably successful for microelectronics, but it's incredibly poor for optics. And why is that? Because silicon has a band gap of 1 electron volt. So at high powers, you have 2 photon absorption at 1550 nanometer. And this was long realized, and there's a new material that was really pioneered by Michael Lipson at Cornell, and that is silicon nitride. And silicon nitride is a material that has many, many beneficial properties. It has an index of refraction higher than silica, about 2. It has a band gap of 5 electron volts, so it's transparent down to the visible. It has a very high damage threshold. You can propagate 10 watts of optical power through a silicon nitride waveguide without any damage, without any Raman, without any Bruon. So it's very striking chemical properties. It's a CMOS certified material. It's been used in CMOS for many decades as an MCAP layer and also as a stressor layer for transistors. And it will have no 2 photon absorption at 1550, plus it's phase compatible. Now, why took it so long, actually, to discover silicon nitride for optics? The problem with silicon nitride is that the material tends to crack. So if you deposit it with LPCVD, it develops very high stress. And that's exactly why it's used in CMOS as a stressor layer. But for optics, we don't need a few tens of nanometer layers. We need layers that are a micron or have a micron thick. And that's generally very challenging to manufacture. Now, over the last years, there's been a lot of progress, of manufacturing thick silicon nitride waveguides that can reach heights of up to like a micron or even more. And in fact, this worked so well that we commercialized some of the technology with a company that I co-founded about 6 years ago, Ligentech, and we are taping out actually silicon nitride commercially for customers ranging from bio to LiDAR to quantum that are interested in using these devices for different kind of purposes. Now, importantly for this talk is that silicon nitride is an ideal material, has very beneficial properties, for optical microcomb generation. And here is a spectrum that was derived from one of these silicon nitride resonators, a few tens of micron diameter. You see the bus waveguide that brings the light, to the resonator. We can generate here a sequence hyperbolic spectral envelope soliton, but the soliton actually is so broad that it extends into the dispersion regime where the waveguide is not anomalous anymore, but normal. And that's actually why we see this feature here, which is called the dispersive wave, also called for the expert Soliton Cherenkov Radiation. And we can thereby extend the spectral bandwidth actually of the optical comb. Now, one thing I want to draw attention to is that the spectral envelope, including this dispersive wave and the duration, we can very precisely actually predict numerically by using this Lugano-Lefebvre equation with the dispersion operator, with a Raman effect that's actually quite weak here, and also with the Kerr nonlinearity. And so we have very good predictive power of predicting the spectral envelope actually of these combs. And so, for instance, by dispersion engineering, so by changing the waveguide height and width, we can also, for instance, make a comb that's a full octave and has 2 dispersive waves on each red and blue side of the optical comb spectrum. And again, this shows also the advantages actually of this lithographically defined photonics, because you can simply by changing the waveguide height and width, change the dispersion properties. And you can make many devices on a single wafer. Now, so this was this observation that one can generate also solitons stably on a photonic chip opened many, many application domains of these microcombs. And some of them I will want to highlight. But there's been one caveat, in this work, and in this early work and in many other labs in the world about 5 years ago. The power levels to generate a spectrum like this were about 10 watts of continuous wave power. So these are very high powers that are certainly not something that's compatible with chip scale integration. And so what is generally the challenge? So if you go to a conference of fiber optics, then in fiber optics we have a really strikingly low loss. Loss in optical fiber, 0.5 dB per kilometer. And especially in the post-COVID area, I think all of us appreciate the development of low-loss fibers for very fast internet and for transatlantic communication. They go really back to the groundbreaking work of Kerr, who really understood, okay, what are limitations, okay, in optical fibers, in this case resulting from OH impurities, resulting from transition metals. If you look at integrated photonics, despite the commercial success of silicon photonics over the last decades, despite using some of the most advanced foundries like Global Foundries, TSMC, the losses in integrated photonics until a few years ago were dB per centimeter instead of dB per kilometer. So there was a 5 order of magnitude discrepancy what you can do with an optical fiber compared to what you can do on an optical chip. And now you can ask yourself the question, where does this discrepancy come from? Is it fundamental? And can we build low-loss integrated photonic circuits that can kind of close that gap, okay, of optical fibers to integrated photonics? And so the major challenge in integrated photonics is the much smaller mode diameter cross-section that leads to scattering. And you have to address the question of how to reduce the scattering and also how to use a material that allows and admits low losses. And what we developed over the last years has been a process that allows to create very low loss integrated photonics based on silicon nitride. And I want to share briefly how this is done by showing 2 pictures. Okay, one is an ornament here from Damascus, okay, and the other one is a cross section that runs vertically, okay, through a typical microprocessor, be it AMD, be it Pentium. So if you look through a microprocessor, what you see is you see interconnects. Okay, this is cross section. These are metal layers. And the way these metal layers are deposited and manufactured in semiconductor microelectronics is by making a trench, okay, and depositing copper and polishing. Okay, and that's why this technique here is also called basically the damascene process. Okay, in recognition of the copper damascene process used here to make these ornaments. And so we adopted that process for integrated photonics. And so how does it work? What you do is you take a glass preform, so this is a wafer, okay, an oxide on a silicon wafer. You pattern into the oxide little waveguides here, okay, and you fill these waveguides with silicon nitride. And the key advantage of this process is that it allows us to overcome the very large compressive tensile stresses of silicon nitride. Whereas silicon nitride you deposit on a blank wafer would crack within a few hours at a height of 800 nanometers, it does not crack if you actually fill these preforms. When you then polish, okay, in the end you have waveguides. And these waveguides are crack-free, high yield, very low loss, but they're not yet low roughness. Because the roughness you have in the waveguides is still determined by how well you can actually etch, okay, the waveguide preform. And here you can use a little trick, okay, of fiber optics. Optical glass starts to melt at about 1250 degrees, that's a glass softening transition. Silicon nitride actually melts only at 3000 degrees. So what you can do is, you just take a preform and slightly actually heat it up to the glass transition temperature. At that moment, you remove all the roughness. And in this case, you get integrated photonic circuits that are not at the level of optical fibers, but they are a factor of 100 improved of what can be done in the best silicon photonics foundries. And this is an example of such a waveguide. This is a 5 by 5 millimeter chip. And what's shown actually in the upper part here, that's a 1 meter spiral. So it's 1 meter path length. Okay, that's folded here in 2.5 by 5 millimeter. Very compact due to the high refractive index. And the losses that we have for such a spiral is 1.5 dB per meter. Okay, so these are very, very low losses. If you translate them to quality factors of resonators, our resonators would have quality factors in the range of 37 million across actually the wafer. So very high quality factor microresonators. With this, you can reduce the threshold, which scales quadratically, of these parametric oscillators, literally to values, okay, of just a few milliwatt. So that's compatible with an on-chip laser, with a DFB that is hybridly integrated. What are the applications? So these solitons and photonic integrated resonators, along with the very low losses, have allowed many kind of applications. I'll highlight some of them that we explored with colleagues. You can use them for coherent communications, experiments with Christian Kuse's group already 5 years ago. You can use them for astrophysical spectrometer calibration, where you use the large line spacing to calibrate line-by-line spectrographs. we've shown that these microcombs can also be used as massively parallel sources for FMCW LiDAR. So it's a coherent LiDAR ranging technique which gives you in each pixel velocity and distance, and each of the required laser lines requires to be chirped, and we've shown that actually the Solitons can be chirped with megahertz actuation bandwidth over gigahertz range. And there's another application of these microcombs. You can use them for neuromorphic computing platforms, but also make devices that are very integrated, either integrate lasers or integrate other functionalities such as MEMS actuators for very fast frequency tuning. And so all these experiments share the maturity of the silicon nitride platform and also the ability to achieve very low power thresholds. Now, with these very low loss integrated photonic circuits, we can address the last challenge that I mentioned, which is to also have the laser integrated. And for this, we use a slightly different piece of physics. We use the technique of laser self-injection locking. So what's shown here is a microresonator that reflects a portion of the light actually back towards the bus waveguide. What we place here is a laser diode, okay, DFB. And when we tune DFB current, what we see is that there's a region actually where you have self-injection locking. So where the laser current, okay, does not change the frequency anymore of the pump laser diode, but where it's locked actually to the optical resonator. And this technique is called self-injection locking. It's been widely known for many decades. But what's new here is that we can operate self-injection locked and at the same time also generate these dissipative Kerr solitons. And so thereby we can manufacture a very, very compact microcomb that is literally has a power requirement of electrical below a watt, and only comprises here this 5 by 5 millimeter kind of window. You can even go one step further to show you kind of how far we've pushed integration. This is work we did with John Bowers in Santa Barbara, where we've integrated the lasers not using hybrid integration by chip-to-chip coupling, but by heterogeneous integration. So what's shown here is a device where you have a silicon nitride layer, then you have a silicon interposer plus a 3-5 chiplets that are bonded actually on the wafer. And in this case here, we have integrated, so the entire device here is 300 micron height and about 500 micron here in the width. And it shows you kind of the ultimate kind of integration that is possible by combining silicon photonics with heterogeneous integration and this low-loss platform. And so on this wafer here with John Bowers, we for instance demonstrated that we can manufacture on a single kind of 4-inch wafer more than 3,000 laser Soliton microcombs. And so it shows you that in principle the high volumes can be attained with this integration technique. Now, summarizing, let me mention that these microcombs have many applications where phase stabilization is not required. Okay, be it low noise microwave generation, be it very fast distance measurements, be it LiDAR or also OCT or dual comb spectroscopy, which you can do also with free running devices. But more generally, in the process of studying these microcombs, what we've discovered is that the silicon nitride integrated photonic circuits have many more applications than just microcombs. They can be used to make very narrow line width frequency agile lasers. They can be endowed, or can be used also as parametric amplifiers. They can be endowed with lithium niobate for making very fast modulators using bonding, or implanted using erbium to make amplifiers. So it's a very useful kind of platform to work on, and that's precisely also why we started to commercialize silicon nitride a few years ago with Ligentech. And to give one example, this is a paper that came out in Nature from Xanadu, a Canadian quantum computing company that has used our photonic integrated circuits for pair generation for photonic quantum computing applications. And so it shows that the application space is much larger than just the microcombs themselves. So with this, I'd like to conclude. I mentioned that microcombs today can be generated on chip using wafer scale processing. And we've really taken the technology from the lab all the way to the point where the silicon nitride is now commercially available. It's being manufactured actually in sites also in Germany, XFAB, and in Erfurt, that allow to tape out these large-scale PICs based on silicon nitride. And we're continuing to add functionality, be it erbium or be it lithium niobate, to make frequency agile, fast tunable integrated photonic circuits that in particular address this challenge of making optical frequency combs on chip. And with this, I'd like to thank you for your attention and close by noting and acknowledging the many gifted co-workers that have worked in my lab over the years, and also the collaborators that we enjoy working with, and you for your attention.
Thank you very much for this very interesting talk. Oh, questions? So optical fibers are traditionally pumped or used at 1.5 micrometers because there's the global transmission minimum. Does this also hold for silicon nitride?
Yeah, that's a very good question. The exact minimum actually is not known. I mean, in optical fibers, it's a combination of Rayleigh, so frozen density fluctuations on the short wavelength side, long wavelength side is phonons. What we do know is where the phonons are in silicon nitride. In fact, transparency window towards the mid-IR is wider than silicon. So the phonons kind of start hitting at about 5 micron in the case of silicon nitride. What we know, I can tell you, is the following. We have done measurements to find out what is the residual absorption of photons at 1550 nanometer, not scattering. And we know the fundamental absorption loss of silicon nitride is still 2 orders of magnitude away from where we operate today. And we have an idea of where the issues are coming from that we would like to address, because our aim is to really close that gap towards the fundamental absorption limit. Generally, however, silicon nitride should be, there's no reason why it should not be as transparent as optical fiber towards the UV, except for the fact that there's a band gap difference, 5 eV versus 9 eV. So we should still be transparent down to 700, 800 nanometers, similar to fiber, but then we will see Rayleigh scattering.
Okay, further questions?
Thank you, and I have a question to the first slides. You said that mode matching or mode locking mechanism is somehow due to the CW wave inside the string. Is there a hand waving explanation how the CW light can mode lock this solitons?
Yeah, so that's a very good question. So the hand waving argument that one can of course always have is that one can say what's happening here is that you have this is the dispersion operator. So this is the group velocity dispersion, like an optical fiber. You have the Kerr nonlinearity and the two balance. So there's the balance of dispersion and nonlinearity, plus the balance actually of loss of the cavity and the drive that's clipped off here from the slide. So there's a drive term here that you don't see that balancing the loss. So you can think hand-wavingly that these solitons are, again, solutions where there's a double balance. But what we know today, and that's why I want to bring up this image, is, in fact, what is really interesting about these solitons is that they can persist in almost any dispersion landscape. And so here, this is maybe a technical slide I didn't show, but if you have a perfect anomalous dispersion, you have a parabola in your variation of the free spectral range. What we see in real resonators is that there's many perturbations. And you can ask yourself, okay, would a soliton still exist in the presence of perturbations? And what we've seen is that no matter what perturbation you put into the dispersion profile, there's still actually attractors that are stable and give stable waveforms. And so our understanding today is that we shouldn't think about them as solitons, as perfect section hyperbolic pulses. We should think them as stable attractors in a nonlinear driven system. And they exist in normal dispersion regime, in a zero dispersion regime, in the presence of imperfections. And again, generally hunch to this principle that we've seen in nature, that no matter where we look around us, we see order, be it stripes and zebras, be it sand dunes, or be it in this case complex-driven chemical reactions out of equilibrium. Nature has a tendency to create order in nonlinear-driven systems, and I think that's really what we're exploiting. Yeah.
Okay, next question.
Thanks for a very nice talk. And what is the pulse repetition rate? Because you showed, follow up on this self-ordering systems. So what is setting the pulse repetition rate? I mean, you showed actually some results where it wasn't equally spaced, right? How does it shift, if you get a little bit of perturbation with heating and stuff like that?
Yeah, so the repetition rates can be, the highest that has been made is just limited by bending loss of the resonators. At some point you can't confine anymore. This goes as high as a terahertz. And the lowest that these dissipative Kerr solitons have been generated is a few gigahertz, because the lower you make the repetition rate, the less efficient becomes the process of these DKS, because the overlap with the continuous wave background becomes less. So that's kind of the spread in the scales. And in terms, yeah.
But I was meaning in the multiple pulses, because you have multiple
Yeah.
pulses in the ring, right?
Yeah, we can also, so the question is there, if we can generate those multiple pulses, or?
You know, what is setting how many pulses you have in the ring?
Okay. Yeah, so in this graph here, for instance, so how many, yeah. So these are, that's a very good question. So again, we have to go in a bit more details. So generally, this background, these Turing rolls, depends kind of how far, the first cycles are generated. So it's set by dispersion and cavity loss. What is interesting is that this Turing rolls here are not in the region where you form solitons, but you can also form such perfectly ranged solitons, which you call perfect soliton crystals, in the solitonic regime. And then it turns out actually that these solitons are locked to any imperfection in the background. So if there's a bit of scattering, that generates and populates one optical mode more than the other, it will beat with the optical pump field and creates a potential onto which they lock. And we can probe that potential and see kind of how solitons range, also change the crystal lattice, but they still form perfectly coherent combs, except the fact that, of course, the repetition rate multiplies with the number of solitons if they're equidistantly spaced. So there's a lot of, as I said, non-dynamics going on in these systems. What we have learned is that these ideas of that we often have to try to understand the system as a double balance or in terms of Fourier mixing pathways, it really breaks down. These are partial differential equations, and you're looking for solutions. And they allow these stable entities to exist, even with very complex dispersion operators and with very many imperfections.
Okay.